All right, hello, welcome. I've been on vacation for 2 weeks. It's okay. So, Unit 2 will be covering forces. So, um, right. So, what is a force? Sorry about that. All right, here we go. Force. So, what it is, or what it does, basically, it's that it's necessary to change. Like when do you use it? Is to change an object's motion, which will result in an acceleration vector, and a net force will be needed. Will be needed. Without a net force, there's either neutrality or negative force, which means something else, but we're not covering that. Will be needed. We'll be covering it, but not now. Needed. So, what is a force in a basic definition? Easy. A force is a push or a pull. Very simple. Right? It's it is sorry. It is an interaction between two bodies. Remember that? If that's kind of connected to last lesson, is that any type of force will happen between two bodies is needed, or else it can't interact. Like a body interacting with its own, that can't happen. And so that results in a net force between the interacting bodies, which will cause a force, obviously, resulting in an acceleration, which then results in a motion. So therefore, you come up with the statement that when there is a motion, there's an acceleration, and that force will be needed, and it all comes down from a simple thing, which is a force. A simple push or a pull. It can either go against or it can pull. But that's very basic. So what are the different types of forces? Well, there's a lot of forces in the world. A lot of them come down to like subcategories. But the main ones, the important ones really, are the four forces. Okay, there you go. The four forces. So, guess which one is the first one? Boom, gravity. There you go. Gravity. Alright, the other one is electromagnetic. This is a huge force. It really it's like any other force, it will come down to this category really. Any other force. Electromagnetic and all the other forces really are covered in AP Physics 2, which is next year, if you pursue, obviously. But really, in AP Physics 1, most of the forces really are just like tension forces, which obviously come down to either gravity or electromagnetic. And then there's atomic forces, which comes down to chemicals or, well, the particles, hence the atomic name, which is the strong force. Yes, it's called the strong force. And guess what the other one is? The weak force. Yep, that's it. So these are the atomic forces, the forces that contain particles between them, aka neutrons, protons, and electrons. Hooray! So this is basically what maintains the substance structure of the molecular level. Nothing too big. And oh, yes, very important statement about any other force, which obviously relates to the body statement, is that will always, or really simply, it always exists as a pair. All right, never in isolation. Okay? So if gravity is a force, it's acting on something. It can never be alone. Even in a vacuum, it's within the vacuum. The vacuum is empty, but it's still a thing. The vacuum is nothing, but it's still within gravity. Therefore, it's never in isolation. And that goes down to every single force, whether it be the strong force, weak force, electromagnetic force. Strong force is interacting with the other weak force to, maintain each other. Hence why neutrons are now exploding every single day, which is equivalent of a nuke. But who came down with these awesome statements? Well, that's my man Newton. Newton's laws of motion. And nope, I'm not talking about that type of motion, which I have plenty of. Motion. Guess what? There's three of them. Hooray. So, number one. This one's really simple. If there is no force, there's no acceleration. Just like that. It's just down to the statement I talked about before. The whole process is that to change the motion of an object, a net force will be needed. Therefore, a force needs to be equivalent or greater than another interacting force, which is, an interaction between um, two bodies, which I didn't write by accident. Sorry about that. It's either a push or pull. So that just, it's a cycle, and therefore no acceleration with no force. And number one and number two are actually quite simple because number two states that if there is no net force, or sorry, really, I mean, it does mean number one, but number two just means F equals ma. So with a net force, that means there will be an acceleration according to the mass of the structure. Okay. And this can be really simple. If you rearrange it, you can find that the acceleration will be the force divided by the mass, which goes in hand because it depends on how big it is. If you put a force of 100 newtons on me and 100 newtons on a baby, our accelerations will be different. Mine will be lower because I have a bigger mass. Now, keep in mind, mass is not weight, which I think I've talked about before, but mass just refers to the actual, um, in day basis, it refers to the normal force, which is the upper force that goes with gravity against the floor. And so that force gets turned into a Newton equivalent, which is what we see on the scale when we weight ourselves. Whew, so hot. And then number three, this one's quite important. Every force, every single force in the whole universe has an equal and opposite reaction force. Mm. This can be stated with an equation. Let's see if I remember it. F A, comma B, comma means it's acting on, means negative F B acting on A. So that's the actual equation for it. You'll never really use the commas acting on bodies, like maybe in two problems on the AP exam. It's really simple, really. So the statement is that any dynamics problem problem. So this just refers to like forces, right? Um, we will draw. Yes, we draw a diagram. So this is kind of what I was talking about in physics overall, like when I first started talking about the course, is that there's a lot of diagrams and a lot of visualization for a lot of problems, which will be then used to identify all the forces and oops, sorry for the bad writing. Identify all forces and their direction. Remember, forces are vectors, so they have a direction and magnitude vector. And so that we can make a statement, or better yet, a F net statement. Uh, right? To find the net force. So let's say I'm pushing something to the right, 100 newtons, and then friction is pushing to the left, 70 newtons. It has a net force to the right of 30 newtons. And so that will result in an acceleration, movement of motion, etc. And so that is really all to cover with just a basic understanding of force is what it is, and important things. And so let's move on to practice problems. Um, what are we on time? 11 minutes, perfect. So let's start with problem number 1. Okay. So there is a 1.5 kg. Let's see. What should it be? Probably a book resting. A 1.5 kg book rests on a table. All right. Rest on a table. And then after, there is the movement of the table. I think a better example of this would be a cloth and a cup. Let's say you're doing the cloth like little magic trick, really, or when you see like a magician pull a cloth on the table and there's cups on the cloth and they all don't fall. This is kind of what I'm trying to explain here. So there's a book on a table, and then the table, after the table is pulled out really quickly. All right. It's like really fast. Okay. So try describe what will happen to the book and why. Using, of course, Newton's first law. This is a very common type of problem. You'll see this especially in chemistry and physics, is that they'll expect you to explain a type of problem. A lot of these tend to be in word format and not mathematical format, because AP loves like messing with you like that. Like they'll never give you a number, they'll give you a letter, they'll give you something, and then yeah, you're on your own there. And so, using Newton's first law, how can we describe what will happen to the book if a table is really pulled out quickly? So, what is Newton's first law? Well, here it is. Newton's first law. We can just scroll up, or we can just remember that if an object stays at rest, it an ob- an object stays at rest unless acted upon a net force. All right. So, if a book is just laying on the table and we pull the table sideways really quickly, so quickly that basically does not interact with the book whatsoever, what will happen to the book? Well, for a moment, it will just stay in place while the table moves under it. And then obviously it will fall, right? But what is important to know is that the book didn't slide off with the table, right? Obviously, there's real life scenarios of friction and all that, but you've seen it happen, or you've probably seen it in real life. Like, let me just draw this. There's a table, then there's a cloth, and then there's like a cup, right? If you pull this cloth like really quickly, 100 meters per second, the cup will just fall down and like wobble a little bit, but it will remain in its same place. And that is because the thing was moved so quickly that there was no force acted upon it, because obviously it didn't get to, because the force was not acting upon the object, therefore resulting in no net force. And according to Newton's first law, an object stays at rest unless acting upon net force. No net force, nothing happens. It just stays there. Obviously, it will fall down, but that's due to gravity, which is a net force. So we can just write it down, is that the book will remain in place due to inertia. Inertia is the capability of mass to not move or resist movement, aka motion, aka forces, due to its mass. And inertia is another name for Newton's first law because it defines the same thing. While the table moves under it. Okay. Obviously, after the book will fall due to gravity, but within the same position. It did not slide off, all right, comma, because of friction, slide off with the table. So you'll notice that if you do it really slowly, you're putting a major force towards the like book or cup, let's say for example, and then you actually start dragging along it, and that's due to friction, and that's just because of the mu factor, blah blah blah, and velocity. So the slower you move something, the higher the friction variable will be along with other object. So yeah, you just have that. But the faster you move something, the less time it has to interact with the other object. Therefore, you'll have it do this kind of like, not phenomenon, but it just slides off. So problem number 2. This one should be pretty simple. We'll just go along with everything we learned today. So the first one was Newton's first law. Now this is Newton's second law. Let's say a 4 kg object is pushed with a net force of 10 newtons to the right, because it needs a direction. Okay. So now you will have to find 2 things. First step, what is the acceleration of the object? Okay, and then part B will be how far will it travel? It travel in 3 seconds. All right. I'll give you a little hint here. Starting at rest. So a 4 kg object, so a 4 kilogram object is pushed to the right with a net force of 10 newtons. What is the acceleration and how far will it travel in 3 seconds starting from rest? All right, so think about that for a bit. Okay, there you go. Boom. You thought about it. So how can we get acceleration? Well, first, obviously, read the problem, state down what we know, what we don't know, and what we need. So we need acceleration. And what we have in the problem, we have mass, which is 4 kg. And then we have a net force, aka a force of 10 newtons. So what type of equation do we have or can we use that has F, M, and A? Well, obviously, Newton's second law, F equals ma. You have 10 newtons with a mass of 4 kilograms, and then you divide this by 4, and you end up with 2.5. 2.5 meters per second squared. Remember, the units is what matters the most. So this is for part A. Part B. This comes down back to your favorite unit, kinematics. Perfect. So we use kinematics. Let's see if I remember which one to use here. What are we finding? The how far? Okay. So we use D equals VOT plus half, yes, half AT squared. There you go. So what can we do to modify this equation? Well, first it's starting a rest. So all of this equals 0. And then we have the acceleration and we have the time. Perfect. So the distance will equal half of the acceleration, 2.5, times 3 seconds, which is the time, squared. Then you put all this into your calculator. Boom, boom, boom. Okay, there you go. And you'll get 11.25 or 11.2, 11.3 meters. That's how far it will travel with a net force of 10 newtons of a 4 kilogram object moving to the right, obviously with no friction, in a span of 3 seconds. So that tends to be an easy problem. A lot of people actually forget to use Newton's second law, because later on in physics you'll be rearranged, like you can rearrange like really big equations to equal either acceleration or mass or force, and then you put that big equation into the actual F equals ma to solve for another variable, and sometimes it simples down to a really simple thing, but people forget that step and they get caught in this loop of trying to solve an equation with two unknown variables, which obviously is impossible. So Newton's third law. Let's say I push or you push against the wall with a force of 10 newtons. There you go, boom. Actually, no, 100 newtons. Because you're super strong. So, two questions here. What is the force that the wall exerts on the student? There you go. And part B, why doesn't the wall move? Why is the solid, unmovable wall not moving? Okay. So, part A, remember, Newton's third law, FAB, or you can just, use your brain, is that any force will have an equal and opposite reaction. So, let's say A is the student and B is the wall. I have a force of 100 newtons acting on the wall. So A to B. What will the equal and opposite reaction force of the wall be on the student? You're correct, negative 100 newtons. And this just refers to the actual direction of the force. It doesn't actually have to do with quantity. Remember, with forces, yeah, they're vectors. Therefore, the sign doesn't refer to the quantity, it refers to direction. Okay? So the force that the wall exerts on the student is negative 100 newtons to the left, depending on where you push. But it will be negative 100 newtons. So why doesn't the wall move? Okay, well, it's because the actual wall is connected to the earth, which has a huge mass. Therefore, that that force that is, mm, well, that is true, but on a simpler basis, on a simpler way, not to connect it to earth, but it's just simpler to say that the force is not strong enough um, to overcome friction. I think that's a simpler overcome friction. In this case, it will be static friction. So that's just a simpler way of saying it. So the force is not strong enough to overcome the static friction of the wall, and also because the forces are neutralizing, right? Because you have a force of 100 newtons to the right, force of negative 100 newtons to the left. Therefore, there's no net force. Therefore, there's no motion. So you would have to either A, have a force strong enough to, overcome friction, or B, just destroy the wall. There you go. And then we can just do a few force problems. These are the push and pull kind of things I was talking about. So let's say a 5 kg box is pulled to the right across the floor. No, the frictionless floor. Frictionless floor. Yeah. By a rope. Did I mention direction? Yeah, to the right. By a rope with a tension of like 20 newtons. There you go. So tension is just another way of saying the force within the like the rope or string. Tension is a really really common force. Well, not force. Sorry. Um, like interaction. You'll see. It's just another way of saying, oh, what force is within that string. You can easily say, yeah, it has like 20 newtons to the right, but the actual name of it is tension. The tension within the string, or the rope in this case. So, simple question. What is the box's acceleration? Okay. So, first, we'll begin with a free body diagram. This is something you will be expected to do and you should know, and it will help you across all your career. You draw a circle, okay, and then draw down the forces acting on it. This circle is just the center of mass, basically. It's just the object that you're trying to describe. So this little circle is just a 5 kilogram box, and it's being pulled to the right across friction. That doesn't matter. What matters is the force itself, pulling to the right with a force of 20 newtons. So you'll draw an arrow to the right, and this will be called force T, which stands for force of tension. You can call it T, you can call it whatever you want, really. I just use any type of force. You use the force itself, the variable, then with a subscript of whatever the thing is. And sometimes you'll have FT1B, FT3BA. Like you'll have these huge variables with subscripts that go like 3 levels, but that's just how it is. And then in this case, those will be equal to 20 newtons. Just be familiar and able to bring a ruler and also comfortable with just using variables instead of numbers, because that is how you will be doing it. So there's no friction, so no opposite force. This just means it's going to be moving to the right forever. How can we actually find that movement, that acceleration? Well, what do we have in this problem? We have the force, we have the mass, and we're trying to find the acceleration. There you go, Newton's second law, F equals ma. So the force is 20 newtons, the mass is 5 kilograms. There you go, divided by 5. Acceleration of 4 meters squared per second. Sorry, 4 meters per second squared. And that would be the acceleration to the right, which is that's positive, but you can also draw a little vector. And last question for today. This will be, is this okay to do? Yeah, I think this will be fun. This is a tension between two different objects instead of just a tension on one object. So let's say there's two boxes. There's a 2 kg one and 3 kg one. These two boxes are connected. Wait, pause. Yeah, sorry about that. Someone came into my room. So there's two boxes, 2 kilograms, 3 kilograms. These two boxes are connected by string with a tension force of 15 newtons. This is pulling to the right. This is a frictionless surface. Okay, keep that in mind. So, what can we do here? Well, the first thing to do would be to draw a free body diagram. But how can we do that if there's two objects? Well, the easier way to do it would be to combine these two forces. These two masses. So you'll have M total, which equals MA plus MB, which equals to 2 plus 3, which MT equals to 5 kg. There you go. That's simple. Okay. So you can just draw a diagram if you want. This is how it looked later on in real life. In later physics. So you have M1, M2, and then you have this tension force. But in here, we can just use basic equation. So since we have the total mass and we have the force and we're trying to find the acceleration, really. Oh, sorry, I did not ask for the questions. Oops. What is the system's? All right, that's important to know, the system's acceleration, because the acceleration could be different. Obviously, it's not going to be here because they're the same object, frictionless. Um, Depending on its mass, obviously, it will be different if you were to pull on one specifically. But so, what is the system's acceleration, and what else? What is the tension? That's a good one. What is the tension? What is the tension force? What is the tension force between the boxes? This one's good. This has to do with the diagram I just drew 5 seconds ago. So easily we can just do AF equals MA. Force is, what was it, 15 newtons? Mass is 5, acceleration divide by 5. Acceleration equals 3 meters per second squared. Okay, so that's the acceleration. What is the tension force? Now this one's good. Okay, so what would we do here? What is the tension force? What is the force of the string pulling it? Because that is stated. Wait, why is it stated? Oh no, between the boxes. Sorry. So this is where you would have to draw a diagram. frictionless surface, two boxes. Sorry, I got confused there. So we know this Ft equals 15 newtons. But now we're trying to find this tension force in between the actual boxes. So what will we do here? Well, let's state what is actually going on. If it's moving to the right, we know that the system's acceleration is 3 meters per second squared. So that means we know the whole thing is moving to the right. Pretty slowly, but we know it's moving to the right. Therefore, that means the mass too. Okay, well, the force technically does kind of matter. But let's just say this one is the 3 kilogram one. And then, yeah. Let's say this one is the 2. Let's say M1 is 2 kilograms. Okay. We have to state that because the actual thing will be different. So we have a force, Ft, that's pulling to the right, but we know that any force will equal to ma. So we can do Ft equals to ma. So this is a totally unknown problem we have here. What does Ft equal to? But actually, we know the mass of the object, but how do we know how much it's accelerating by? Well, we know that the acceleration of the system, the whole thing connected, is 3 meters per second squared, and there is no friction whatsoever. So what would it be to say that the acceleration is different? That's because it isn't. The acceleration is the same. The acceleration of a system will be the same unless acting upon another net force. That is Newton's first law. So you insert it there. And you equal it 2 times 3, 6. So the force of the string, the tension force between the boxes, is a total of 6 newtons. All right. So let's just review shortly what we covered today. We covered forces, aka dynamics. So what is a force? It is a push or a pull. It's an interaction between two bodies. What's it needed for? It's needed to change the motion or acceleration in net force, and that will be needed to actually make it move. What are the four forces, or the main ones really, is gravity, electromagnetic, which is kind of this force that it's just anything else that's not gravity, or the other ones, the strong force and the weak force. These are the atomic forces. You'll never recover them. And then keep in mind, forces will always exist as a pair, even if you don't see it. Like, for example, when you stand up, there is a force called the normal force that acts upwards. And then there's the gravity force, which is pushing you downwards. But what is that normal force from? It's from planet Earth. It's pushing upwards on you to counteract the gravity pulling you downwards, or else you would just sink into the Earth. And because the mass of the Earth is so massive, massive, it literally does not move. All right. So that's why we can all just stand here in peace. And it's never in isolation, even in a vacuum. So, what are Newton's law of motion? Well, there's three of them. Number one, if there is no force, there is no acceleration. In a more detailed manner, I guess, if you really want to, if there is, I wrote it down somewhere actually. Here we go. An object stays at rest unless acting upon a net force. So, there you go. Second, F equals ma, or F net equals ma. That just means that any force will be equal to the mass times the acceleration of the object. And then the third one is that every force has and will have an equal and opposite reaction force. So if let's say you push against the wall will push back, or else you would go through the wall. That would be bad. And then any dynamics problem, we will draw a diagram. This is called the free body diagram, FDG, free body diagram, free body FBD, sorry. And this is to identify all forces with their directions so we can make a statement. I guess a more detailed example would be, let's say I'm pulling a ball upwards, and then I'm actually pulling it at an angle. You wouldn't draw this one. When you're making FTG, you never draw the actual angle of force, but you'll draw the components. Or really, like, you'll draw the actual angle in the normal like statement, but you'll also draw this components, which is what we covered in the last lesson. So you have the x component and the y component, and those are the things that matter. And those can just help you, like when you want to isolate an object in a big system. So let's say I have a pulley system that has, I don't know, a rotationally wheel that for some reason has friction. Oh no. And that wheel is pulling two different boxes, which also have friction against the wall. One is going down, one is going upwards. And guess what? The other one's in incline, the other one's in free fall. There you have a bunch of things going on. You want to isolate one different thing, you use a free body diagram to identify the forces and the interactions between the bodies and within the same system. And so these practice problems, hopefully they helped you. And thank you so much for watching. Make sure to check out my other videos and have a good day.